Hi guys, we will be looking at uh, setting up and calibrating a, an eddy current equipment. In one of my videos, I compared the Eddycon brand with the Olympus brand for eddy current. But today we'll be using the Eddycon C, which is a miniature version of Eddycon CL. So we'll just be looking at the interface and also how to set it up, the buttons, what are they for. Then we'll do the basic calibration. From there, we'll just look at some things you need to look at for while calibrating this the current unit. So before we start, the on and off button is on the side. So it's on right now. If I turn it, it goes off. Unlike the Eddycon CL where the on button is on the front face. So now we put it on. So the unit is on, coming up. Eddycon C, the version of the software. So like your typical display for the Eddycon ECT machines, you have your impedance plane and your time base. Just to give a little explanation of the two so that you understand the concept. Okay, before we start the calibration and looking at the Eddycon CL unit, I'll just explain this concept of the impedance plane and the time base. So this is our 00 axis. Based on the setting which we will look at, you can put this your 00 axis at different points. I can decide to put it here, I can decide to put it up. So it depends on the setting. But in this case, we are looking at it being at the center, which is 50-50. 50% on the X axis, 50% on the Y axis. So it comes straight at the center of the impedance plane. So what happens in your typical impedance plane? Here you have your SL. We'll talk more about this on our eddy current training in other areas, which is your inductive reactance, and here you have your R resistance. From the days of physics, you know that when you combine both of them, your SL and your R, the vectorial sum will be your Z, which is your impedance. So your eddy current curves that will be coming, your indications that are coming here, basically call them the impedance curve. So if I get an indication from an eddy current probe, which could be as a result of the change in the inductive reactance or the resistance of the material, definitely a curve is going to come out. It depends. The curve can come this way, the curve can come this way. Depends on your setup. This is your impedance plane. So whatsoever indications that are coming at, whether it is due to the curvature of the material or due to the surface of the material or due to the weld toe or weld cap or whatever surface indication, or even due to real defects like crack, they are all going to display as changes, as curves that will be coming out on your impedance plane. Now, for those of us that maybe peradventure you've tried doing eddy current before, you discover that after some time there will be so much curve in this impedance plane, and you get confused, and you're wondering what is what. Is can be a problem. So one way to unravel the mess, that so-called mess in this case, that will be created by a whole lot of impedance curves that will be coming up and intersecting with each other, is having this time base. So basically what it does the time base do? It's tracking, it is tracking changes in the impedance to time. So let's say while we are at 0.00 at the beginning, there is no curve coming. So at time zero, there is no cough. At time, say 2 seconds later, a cough came out here, which means it has led to change in voltage or change in impedance. Something will spike here. It depends on the direction. This spike is telling you that there is a change in voltage. And as we will see during the test, we will find out that this change in voltage is going to coincide with a change in impedance in the impedance plane. So if you are even confused while you are scanning and you are having a lot of cough, if you keep keeping your attention on the impedance plane, when something substantial comes up, it's going to show on your time base. So the time base is very key if you are scanning. It makes it easy for you to monitor your impedance plane. Then for Eddycon C that we'll be using, you will find out that you can freeze this machine, you can stop it and replay whatever you have recorded. That way you can easily track with the cursor, you can track the time base and the corresponding impedance coverage you are going to get. This way you are able to know if what you are getting is a defect or not. So that is just to get a clear view on this before we go to the calibration proper. So back to our unit now. So you can clearly see the impedance plane and you can see here the time base. For Eddycon C, the time base has a red and a blue. The red, one of them I'm not sure until I start. One is for the x-axis, one is for the y-axis. So if I have a curve that comes and spikes around this area, we will know based on the spikes that are coming on the time base, whether it's from the S or Y, or in some cases, both of them will bring out a spike. So let's do an overview of this unit. If you've understood the basics of eddy current, you will always know this button they call the zero button or the balancing or the null. Now, by design, every eddy current unit is a bridge circuit, like we did in our if you did some form of electrical basic electricity where you have a bridge. So here you have an indicator. In one of these, in the case of an eddy current unit, this is your probe. And we all know that in a bridge, if there is a change in resistance in any of the, so this is R1, R2, R3. If there is a change in resistance in any of these, even this probe now on its own is a resistance. So if there is a change in any of these resistance, it's going to affect your indicator. So if I have an eddy current probe and I bring it close to any material, because the coil in this probe is interacting with the material, there will be a change in resistance or impedance as the case is now, and that will lead to unbalancing of your bridge. So we always have this one button in the machine that will balance the eddy current unit. So the whole concept of balancing is if there is any change in resistance or impedance of the system, by the time you are ready to do your check, you need to press your null or your zero or balancing. As you can see in the machine now, it's telling you that it is balancing. Let me take it again. It's telling you that it is balancing, which means it's trying to cancel out whatever reading or whatever indication, maybe due to moving the probe around, you have cancelled it out. Where should you balance? This is very key. You will balance anytime you take the probe from your material and you put it back on. You must balance again. That's point one. If you get to the edge of the material and we have this whole edge effect happen, we talked about edge effect some other time, and edge effect happens and you want to scan around that area, you have to balance again. Then sometimes you may have done a lot of scanning and your screen is becoming so filled with with curves that you are getting confused and you don't know what to do, the best thing for you to do is to balance again and send everything back to zero. Then the last reason to balance, if you change any fundamental function or data or value in your machine, you must balance it for the effect of that your change to take place. For example, if you change frequency from 100 kilohertz to 200 kilohertz, that is a significant change. If you don't balance it, the machine does not know. The machine will keep working with the 100 kilohertz that is there for. But as soon as you balance, the machine automatically resets and taking the new variable and continues from there. So that is very key. So this is the balancing. Then you have your F2 button. If you remember, I told you by default when you turn on the machine, it will show you your impedance plane and your time base. But if you look at it as I'm changing F2, it's changing my screen mode. It's changing my screen mode. So this is giving me form of waves. This applies when we are doing a rotary scan for both inspection. It comes like wave. So when your indication comes, it comes by wave. We will talk about this in subsequent videos. If you come to this is full screen. This is very good when you start scanning and you don't want, because especially for this miniature version of an Eddycon C, that the screen is very small. If you use a full screen, it gives you more view and are able to see the differences. Then if I continue to press, this is only the impedance plane without the time base. This is where we started from. So F2 changes the viewing window. Then this, your point, it's wherever your cursor is, when you press F3, it cancels whatever time base and starts fresh. Then we have this, and even intuitively, when you look at the machine, let's say you are a first-time user of this equipment, intuitively, if you have idea of concept, because it's always very key that before you start doing eddy current in the field as an inspection method, you need to get a sound theoretical background and get some basic understanding. Yes, you will have some challenge. So if you look at this symbol, the way it's even looking at, you know, there is direction and there is a form of an angle. So you know that this is for changing the angle. If you look at this step sign, you will know if you have dealt with some of this NDT method, especially like UT, you know that this step means increase, which has to do with your, if you want to increase the steps of any, how each value is read. I'll give you an example. If let's say I come down to gain, I'm in gain now. You can see my gain is is 9 dB. If I press on the step, you will see I've now had plus 10. What it means is that if I do increments, my increment will be coming in tens. If I press step again, you see my increment is going in 0.1. If I press step again, my increment is going in in 1. So which means I had 9 dB here before. If I press plus to increase it, I'm going to get 11 dB, 12 dB, 13 dB. Okay, so it's increasing by 1. So this is the whole idea of this step. Why is this step very important? If you are impatient, you cannot wait for your values to be increasing, maybe by values of 0.1 or values of uh, 1 or 2 or 5. You want it to be increasing by 10 or 100 so that you get to where you are going fast. You increase your step and you increase the value easily. Plus and minus, whatever the value is, if it's a numerical value or you want to select or change, plus or minus, you use that to change the values. Your up and down button, if you want to go down this menu, that's where you press up and down. You can see as I'm pressing it, it's moving up and down. It's moving up and down. Check, this check sign is to enter. So let's say I have a value, I'm increasing this value and I get to where I am, or I press this is plus 6 dB. If I get what I want, I press check. It saves the value, it accepts the value. If you want to cancel the value you have put before, you use this cancel button, which is the X. These are buttons basically to work around the interface. Then the next key buttons you are going to see on this unit, this is your home screen. This always, just always remember when you see this three curve, the basic symbol for ID currents, if you look at the board, whenever you see this symbol like this is the basic symbol of eddy current. I will talk about this shortly before we start doing the calibration, but this is the basic symbol of eddy current. So wherever you are in the screen and you are confused and you are lost, when you punch on this button, it takes you back to the home screen. So every other button you are going to press in this place are going to take you out of the home screen. To get back to the home screen, you need to press this button. So if I press this settings button now, you see I'm out of the home screen. If I want to get back to the home screen, I need to press this button. It takes me automatically to the home screen. So this button is very important. Then this button, in some equipment, they call it the freeze button. This machine, where it is radically different from Mentor EM and Olympus Notec 600, is those machines, they have the freeze button. But if you have recorded values or you have scanned for some time and you want to view those scans that you have done, you press search. It will go into a mode such that you can scroll. So if I scroll down, if I scroll plus and minus, it will start it will start showing me readings that I've taken before. So we'll use this search button later when we want to do analysis. And because this machine has the ability to save data properly, it's also very useful when you want to review a saved data that you've acquired. Let's say you have a long word length, and you have scanned the entire length, and you want to review the information that you have scanned. You use this search button. This one is for saving if you want to save. So you can save results and you can save setting. It's the same application for all editing method that require a digital unit, whether UT or eddy current, all their advanced form. You need to save, you should be able to save your setting, you should be able to save your data. It is very important. So that when I go to setting, I can open the setting, I can even export a setting and send to another Eddycon unit. Somebody can be in the office and do a setting and send to somebody in the field. There are a whole lot of ways. Then the result, we can also save results. I don't want to go into that now. We'll look at that later. So let's go back to our home screen and start looking at the actual variables that are there. We will look at each of these items in the unit and understand exactly what they stand for. But to get a better idea so that some of the things we can assess them and the effect of such change, we need to first of all connect our probe. We've had cases of personnel go to work and they went with a bad probe. They did not know. If I take out this duct tape, by principle, this is actually a surface probe, even though the surface is curved and this is a bridge probe. How do you know? If you look at the body of the probe, it's clearly written. But even without being written, normally this is how bridge probe comes. I will talk about that in some other video where we look at the types of probes for eddy current. So you have a coil here and you have another coil here. They are on the surface. What is protecting the coil from being damaged is just this plastic casing. If you don't protect it, which is why we had the masking tape on it, if you don't protect it and you start applying it on surfaces, over time, this surface is going to wear off. And that coil is so tiny and it will cut off. So you always ensure to protect this. So we've had cases where personnel went to feed, damaged this, and covered it back with masking tape, and you are not sure that the probe is working. and you just connect it and you are wondering where your problem is coming from. So normally you have this red dot here, which is supposed to match with this. When you put it, it should click and you know it's connected. So the red dot is matching with this red here. The designers of this unit have done it such that you will not make mistake in connecting this micro dots to another one. So this is 16 pin and this is 16 pin. So the same red matches with the red here. Now, this is the part where you will know if the probe is working. So I disconnect. To know if the probe is working, look at your screen. Immediately you put it, your screen should show some size. See, you see? It shows you that the probe is working because by me connecting the probe, you have seen changes in your unit. So I tried it the third time, you see? This will just tell you. If you put the probe on a unit and you don't get any signal, any glitch, just know that that probe is faulty. It's as simple as that. There is no other test for that apart from going to the lab. But if you put it in your unit, to respond. Also, to know if your probe is working, we have not set anything. So I told you before, if you look, did you see anything? You need to zero first. So if I zero, let's see if something will come out. Zero is balancing, is the same thing. So you can see, you see that though I have not set it to, you can see that you can see some changes on this time base. I balance again. This machine is not calibrated, so there's a whole lot of things that are wrong with the way it's displaying. We'll correct them as we go on. So the first thing you are going to see in your unit is your frequency. So what do? The frequency is actually, in theory, it is the only variable you are going to change here that is external to the machine. So if I change frequency from 100 kilohertz to 200, it is external. It is me that introduced it. But every other thing you are going to do, whether it is gain, whether it is drive voltage, whether it's phase angle, it is the machine that does that correction on its own. So how do you determine the frequency that you are going to use? If you look at a typical ID current probe, if you look at this, there will be a range of frequency. In case if it's not clear to you, the frequency range is from 0.1 to 1 megahertz. That is to say 0.1 megahertz. 0.1 megahertz is 100 kilohertz to 1 megahertz, which means this probe can function between this. So the question is, what should I choose? Should I choose 100 kilohertz or should I choose 100? 1 megahertz rather. We all know by concept, the higher the frequency, the higher the noise. High frequency, high noise, high vibration. So, but high frequency means high sensitivity. If you pick 1 megahertz, everything all over the place, it will be scattered. You will not even be able to differentiate between your normal signal to your noise. Then if you pick 100, sometimes it may be too low. Before now, I normally would advise that you take the middle, which should be what? 500 kilohertz rather. 500 kilohertz. So you put the middle. But a lot of times you will see that when you put 500 kilohertz in some probe, noise, you still find noise around at the 500. So what I normally advise, start from 100 kilohertz and check the signals that will be coming out. If they are not good, you increase to 150, 200 until you get the optimum frequency that works for you. Sometimes for new probes, when you get these new probes, they normally come with a data sheet. And the data sheet will give you the frequency, the optimum frequency that the probe works at. But a lot of times you give the data sheet to personnel, they lose it. And when you lose it, you don't have any reference to get your optimum frequency. So we don't know what's the optimum frequency between 100 to 1 million megahertz. So we play with it. Also, material differences can also affect. So even if you have a data sheet that gives you optimum frequency, you might discover that because the material is a different material, maybe stainless steel or maybe what's it called, aluminum, compared to carbon steel, the results might be different. So it is up to you, the inspector, to determine the optimal frequency. So which means in this case, the first thing we'll do is we'll adjust the frequency. So for this probe is connected already. If I go to frequency now, I take my cursor to frequency. This is where the gain we were talking about the last time. I'm going to 100. So let me first of all take this one to 900, and I take gain, and I say my gain should be increasing by 100, so I can get it to 100. One of the things I told you, after changing, what do? You balance, so that the effect of the frequency change now comes in. So after balancing, let's take it back to so 100 kilohertz, we balance. So this is how my indications are coming at 100 kilohertz. So if I balance, so it's giving me nice clean indication. Now, here is the catch. You can still continue with 100, or you can continue with 200, or you can even decide to say you want to use 500. It doesn't matter. For a technician that is looking for an indication to get, you discover that you need to clearly be able to see your indication. So that is for the frequency. So you keep trying until you get the optimal. I can even continue the process of calibration and find out that that frequency is not working. I will increase it. So what you put in your final report is what you use in doing the final calibration. So preamplification. Preamplification, gain, horizontal gain, vertical gain. If you look at all of them, all their units are in dB. There is a fifth one, which is the instrument gain that is under setting. If I go to setting, I will see another gain again. They call it extra gain. So when you look at this unit, there are a whole lot of gains that are controlling it. So my first advice, do not be so quick to increasing gain. So the first thing you need to do, keep your gain as low as possible when you are starting. So I will come down. If you look at this time-based indication, you can see they are looking very thick. The reason why they are looking very thick is because the gain that you've added is quite thick. Even on the impedance plane, the curve is not coming out clearly. So the first thing, I want to reduce my gain. Let me reduce it to something around 4, 5. Like I said, when you do all these changes, you have to balance. So you balance. So the next thing you go to is your drive voltage. The drive voltage is power. Voltage is power. When I say power, I'm not talking about electrical power or mechanical powers in this case. It's a force. Let me use the word force. It's a force that will be driving your electrical current that is coming into the coil, which means the higher the voltage, the higher the force that is driving the current, which will ultimately affect how your impedance curve come. My advice is do not over increase we have the maximum of 6, so stay away from 6. We can stay in between. Where you are not so sure, be at the middle. So does not have step, so we have 2, 4, 6, so I can stay at 4. Let me balance again and see how that affects. If you see, it's not as rough as it was initially because we have reduced the drive voltage. So the force is not so, because anything that increases the current, that increases, ultimately is going to create more noise. The more force, the more noise, the more voltage, the more noise, the more gain, the more noise. The next thing is our angle. So we'll talk about this shortly also when we start doing a lift off calibration. Then the next thing is filter. For now, for the purpose of this video, I will stay away from filter. I will do a special video on filter. Next thing we are going to look at is the position. When we say position, we are talking about the position of the 0, 0 axis, where the x and the y axis intersect. So if you look at the board, when we say positioning, where our x and y intersect, which is basically this area that we're talking about the other time. So this is the position. So if you look at any time you balance, you will see that your cursor or your dot goes to the position, which means the position is on top. If you look at this grid position, you see it's on top. So if I come to this arrow and I change, you see that it's changing. It has changed from top left to top center to top right. I keep changing. It comes to center right. Here is at center, right? This is actually where we need it. But if we continue to go to center left, it will go to bottom and all that. So let me keep it at center. It goes around again, center, right, center. So this is where I want it to be. Then if I come down to my grid, the grid are these small lines. We call them these graticals, you see. These small graticals, they form the grid. Now, the next thing we are going to look at is the axis. This line of your x and y axis. The dot is here, but the big x and y axis is not showing. But this line you are seeing here is not axis line. It's actually a gate, which we'll talk about shortly. So if we look at the axis, if you look now, we are now having our x and our y axis. So if I balance now, you see my 0, 0 is at the center now. You see it's at the center. So my setup is okay on the axis now. Then we come to alarm. Alarm is otherwise known as a gate. This gate is very critical. If you look at this machine at this point, you see alarm 1, alarm 2. Normally in real life tests, if you are searching and if you set your gate at the end of your calibration, if any serious indication crosses your gate, the alarm will beep. It will make an audible sound. That is if you turn on the audible sound. But if you don't turn it on, the audible sound will not come. So now we have this straight alarm. The best alarm I will advise for us to use is to have the circular round alarm. Why do we encourage the circular alarm? Now let me select alarm until you see. Now this is my circular alarm. Why do we encourage this kind of alarm? So that irrespective of the direction that the curve is coming from, if it crosses the alarm, it will beep or it will show you that this is something you need to take seriously. So we don't encourage this. For example, this you can see this small flat alarm. It's only when the indication crosses this, that's when the alarm. Though we can increase the width of this, that's only when the alarm will ring. So at this other side, the alarm is not going to come up. If we go to the next one, this is no alarm. Then this is the circular alarm. This is the straight alarm that has been there since. It's only when it crosses it on this direction. What about if it crosses on the opposite direction? You may not have it. Or even if it's there, I think the setting took it out of it. You see one on the top and one at the bottom. I can drag the one at the bottom is out of screen. I can drag it up and it comes here. But it only means that when the impedance curve crosses it on the top or crosses on. But what about if it goes on the side? It's not going to capture it. So that's why we're encouraging circular alarm. So this is my circular alarm. We can increase the width of this alarm. You can see immediately I press this check button. Let me press this check button back again. Look at this check button. Look at this screen. You are seeing alarm. There is nothing that is seen again. But if I click on the check button, how will you know that inside a particular function there are other additional functions? You see this small indication here. It shows that there is something under the alarm that you should. If you click on the, if you press on this button, you'll see the alarm. Arrow is the radius of the alarm. So if you look, as I increase the radius of the alarm, you see my circle is becoming big. If I reduce the radius, you see my circle is reducing. You see it, I can do gain and say, how do I want to increase it? I can be increasing. Okay, let's go back. I can be increasing by 10. Now, when we want to do our sensitivity calibration, we want to make sure that this alarm is at 80% of the screen height. We'll talk about that when we are setting sensitivity after doing our calibration for liftoff and setting it. So it's very key so that if you see things under the circle of the alarm, within the circle of the alarm, you don't have to bother. But if you see an indication that is so big that it crosses your sensitivity alarm, it shows that it's something that you need to look at. Then you also, the next thing that you can change is the polarity, which if I keep touching it, it changes the polarity of the alarm. We are not interested in that. The next thing is your sweep. Your sweep is the length of your time base. How long is the time base going to move before it starts overwriting itself? It's just like moving from the beginning of this screen to the end of this screen. If I get to the end of this screen, I don't have nowhere to go. It means I will come back again or come and start from the beginning. That is the whole concept of the sweep. The bigger the sweep distance, the bigger the coverage that you can get as you are scanning before it starts overwriting. So you set it as, if you want to do calibration, you can set it to low value. If you want to do scanning on the feed, increase it to as high as possible. The next thing is your probe selection. Are you selecting bridge? Are you selecting single? Or are you selecting reflection? How will you decide which one you are supposed to select? It's when you look at what is written on the probe. In some other cases, in the cable, you will see it is clearly written. It's clearly written here. If you look at it, is a reflection. But this cable is showing reflection, but this one is showing a bridge. Okay, so this is a bridge probe and this is a reflection cable. So chances are this is going to give us issue during the test. So because they are not matching, your result may still come out, but at some point your indications will not be very clear. Your impedance curves may not be very clear, and it might give you issues. So you need to ensure that the probe is matching with the requisite cable. So we cannot have a reflection cable and have a bridge probe. So you need to correct that. So this is the bridge probe. So we'll choose a bridge. Bridge probes are well suited for where the scan. Then the next thing you're going to look about at is the RPM. RPM, revolution per minute for revolving probe if you are doing both hole inspection. This video will not talk about it because we are not looking at that. So that covers generally for the entire screen. Then additional settings you can see when you press settings here. So here you have your expert mode, your conductivity mode, and your test mode. The test mode is when you are calibrating this equipment by the manufacturer or an accredited calibration company for annual calibration or when you want to do repair. So you don't need this as an inspector, this test mode. The expert mode is what you are using for weld inspection or both hole or any other form of surface inspection.